Okay, same data as yesterday. Remember, we're trying to figure, this is actually very timely, right? They're just trying to figure out right now if they want to make preschool mandatory for all students. I hope they're doing these kind of experiments, if that's in fact the case. We've taken a look at two different groups of kids. One that got preschool, and we're seeing the percentage that have failed, and the other one who haven't gotten preschool, and we're seeing the percentage of those students that are still having struggles in math. Okay, so based on your knowledge of what we did with means, what would be a logical null hypothesis? How would you write this now? Yeah.
PC minus P equals 0.
Yeah, let's think about this now. The difference in their math later on down the line is nothing. There is no difference. Now, I know we don't have any p hats on there. Okay, we're trying to predict for the entire population. Okay, I know we took a couple of samples, that's what p hat stands for, but we're trying to predict for the entire population. Another way to write that, it's okay if you do it this way. It means the same thing, right? I like it this way better. We'll show you why, especially when we draw the picture. But that's what we're saying. We're saying there is no difference. Preschool doesn't matter for math. That's what we're going to assume throughout the entire problem. Now let's just kind of remember what these stood for, right? You got hopefully a good long description there of what it is. The true percentage of students still struggling in math, okay, if they have preschool. This one we said was the true percentage of students still struggling in math if they didn't have preschool. Okay, and you're right. We're going to assume that there's absolutely no difference at all. Now, this changes everything. Remember yesterday when we were doing our confidence intervals, we had to use these p hat values throughout the problem, right? What were these things again? This was like 0.155, wasn't that right? 15.5% of students are still struggling in math that had preschool. And from this sample, was it 235? 23.5% of students were still struggling in math who didn't have preschool, so we had a difference of 8% in our sample. Okay. So yesterday in the confidence intervals, we used those different p hat values throughout the entire problem. We can't do that now. Right here, we're saying that those population values have got to be the same. And they've got to be the same throughout the entire problem. All right, let's talk about what the alternate is real quick. What would the alternate be, DJ, in this case? PC minus P sub P is?
Greater than 0.
Yeah, that's actually what it would be, right? We want to say that students who didn't have preschool are failing at a greater rate. Okay, so you got to be really careful with that inequality. You got to go back to really remember what it means. I guess another way to write that is that, yeah, hey, we're trying to prove that this intervention program's good. Okay, do we have statistically significant evidence to do so? Out of curiosity, what alpha level matches what we did yesterday? Remember, we did a 95%. We did a 95% confidence interval. Now this is one. That's what we did yesterday. 95% confidence interval, right? Yesterday.
Yeah.
Oh, we did 98. Oh my gosh! I mean, really?
That's what it said. That's what I wrote it.
So yesterday's confidence interval we did was 98%. Yeah. Oh my gosh. So what would this percent be that matches it?
0.01.
1%, right? You have 1% on that tail. All right, now. Wow, nobody.
I thought it was.
I thought he had 95.
No.
Okay. Question. Remember 0 was in our interval, wasn't it? Wasn't 0 in our interval? Question. When we get done with all this crazy math we're going to do later, do you think the p-value is going to be lower or higher than 1%? Don't say it out loud. In fact, I want you to do this. It's going to be higher than 1%. Don't peek at your neighbor either. Higher than 1%. You think the p-value will be higher than 1% or lower than 1%? You should know the answer to this question. You're just guessing. No idea?
It is too.
Oh, okay. I was going to see. It is higher. It is higher. Right, 0 was in our confidence interval, right? So we can't reject 0. So we don't have enough evidence to reject. Yeah, the p-value is going to end up being more than 1%. We'll see that when we get there. All right, so what do you guys want to do? We can't use those anymore. Whatever we use as an estimate for the population parameters got to be the same. Whatever we set up our null hypothesis, we have to use it throughout the entire problem. What are we going to do?
There's 0.5.
Oh, no, wait a minute now. So you're saying that these have to be 50%? Our estimates are 15 and 23%. You're going to say that the population percentage of kids failing is 50%? You're thinking about when we had to do that for sample size. Okay? No. We have to come up with a reasonable estimate as to what we think the percentage of kids are failing at. Because we're saying that the people that get preschool and don't get preschool fail at the same rate. Yesterday we used these. We could use them separately as estimates. We can't do that today. We've got to come up with an estimate that's the same number.
Mean.
Take the average of these two?
Yeah.
You okay with that? So how do you take the average? You add them up?
You add them and divide.
And then divide by 2. Somebody throw that in your calculator real quick. Tell me what that average is. 195. Matt, I think we can do better. I think we can even do better than that estimate. So Matt's saying, hey, let's just make our estimate here 0.195, and that's what we'll use in our problem. But I think we can do a little bit better than that. Any other ideas of what we can do? All right, I like this, but I think we can do just a little better. Ideas? It's kind of back in Simpson's Paradox days. We did something, and there was a reason behind it. Yeah?
Did you average out the sample size also?
Yeah, let's think about this now. This had a higher sample size, right? Do I maybe believe in this guy a little bit more than this guy? Somebody see that? Well, let me just do a crazy example. Let's say I had a sample size here of 200, and here I had a sample size of 4. Would you want to treat these with the same kind of weight? No. So anybody got an idea of how we can do a weighted proportion here? Formula-wise? All right, let me give you the formula. This is what we're going to do. We're going to call it the weighted p-hat. Okay? And this is you add up the successes and you add up the sample sizes. So for this particular problem, our weighted p-hat is going to be, what, 22 plus 47 over 142 plus 200, and I think that guy is 0.202. Again, not a huge difference, right? It's not a lot different than just taking the average, but we gave the 23.5% a little bit more weight. And that's what we're going to use. We're going to say, since we say they have to be the same, we're going to say they're both going to be 20.2. That's our estimate based on our sample. And we're going to use that estimate throughout the entire problem. So therefore, we have a different formula for the standard deviation of the sampling distribution. Go to your page 5. You see the formula we had yesterday? Now look right underneath it. It's the same exact formula. They just factored out that thing. We don't have P1 and P2 anymore. We don't have different values for those. We have the same value for both. So they just factored it out. Okay, so our new formula for how spread out all of the values are is the square root of P, 1 minus P, times the square root of 1 over N1 plus 1 over N2. That's how spread out all of the different differences will be. Okay, so let's go do it. Let's see what changes and what's the same. Let's go to our assumptions next. Simple random samples. Anything going to change here? No. But how about number 2? We got a different formula now, right? I mean, by the way, look at those formula sheets. They're trying to help you there. You see how it says for the special case when P1 is equal to P2? Right above that formula? Does everybody see that? Here's what they're saying. Hey, dummy, this is the one you use for a hypothesis test. That's what they're trying to help you. By saying, hey, remember when you did that? That's the formula you use if you're doing a hypothesis test. The one above it, we don't say something like that, and therefore we keep them separate, and you see the formula above it. So yeah, we got a different formula here, don't we? Now again, you can just copy. I'm grading last chapter's test, and I'm seeing people writing down the formulas wrong and doing them wrong in the test statistic. They're on your green sheets. That's inexcusable. So right here, you can just go ahead. Is standard deviation of p hat 1 minus p hat 2 equal to p1 minus p square root 1 over n1 plus 1 over n2? Question mark. Nothing changes over there. 142 is less than 10% of all the kids. 200 is less than 10% of all the kids. Everything's fine there. All right, number 3 is the sampling distribution of, now we have to use the correct symbols here, p hat control minus p hat preschool normal. We know how spread out they're going to be. It's this formula, but will they have a normal distribution or not? All right, what's our formula we have to use here for proportions? It's NP and 1 minus P have both got to be greater or equal to 10. What are we going to do here? Yesterday we used the individual P hats, right? What are we going to do today? We got to use the P weighted, right? Because we said they have to be the same value. So you can even put that in here, right? This is P hat weighted, P hat weighted. That's what we're going to use. So the first one, I don't know if this is the preschool group and this is the control group. So the preschool group had 142, so it's 142 times 0.202, whatever that's equal to. We figured that out. 142 times 0.789, whatever that's equal to. They will both be more than 10. Over here with the control group, okay, same idea, but we're going to be using the number 200, but again, 0.202. Yeah?
What's the check for the second assumption again?
That the sample size is less than 10% of the population size. So in this one, it would be 142 is less than 10% of all students. 200 is less than 10% of all students. Okay, so that's a big difference from yesterday, right? We use the individual p hats here. Not today, because we got to assume that they're the same value, and we're going to assume they're 20.2% as an estimate. Number 4 doesn't change. It's a 2-sample test because the samples were chosen independently. So that guy's just fine. All right, test statistic. Well, that's a formula we use. So that guy needs to be over here. We need to have that test statistic. So one of them we're going to use is p hat weighted is equal to, now we need the correct letters here. So this is going to be x control plus x preschool over the sample size of control, the sample size of preschool. And then our big guy, z-score. Right, we're doing a hypothesis test now, so we need to know how many z-scores that 8% is. So p hat control minus p hat preschool. That's the 8%, right, that we got from our difference. Divided by, and then it's that formula that we're talking about. So here it would be p hat weighted. That's the one we're going to use. 1 minus p hat weighted times 1 over NC, 1 over sample size for the preschool group. This is 8%. This is how much they differ typically in the sampling distribution. Okay, going through our math, I guess we got to show p hat weighted work. So we already did that, but we put that right here. So it's 22 plus 47 over 142 plus 200. That comes out to 0.202. now we got to plug everything into our z-score. So z is equal to, what, 0.235 minus 0.155 over, oh boy, square root 0.202 times 0.798 times square root of 1 over 142 plus 1 over 200. Good luck with that. See if you can get that guy to work with your fancy percent parentheses. Now you got a challenge.
Second number under the first radical.
Okay, so what's the formula say? It is the p hat weighted, that's the 0.202. And then 1 minus p hat weighted, I just did that, that's 0.798. Everybody get a number? You afraid? What do you got? Good. Ooh, 1.17? No.
1.816.
1.816. Actually, you're all wrong, but you got the right idea. I'm going to cheat. I'm going to go to our fancy button. So this is our fancy button for this guy, a 2 proportion z-test. Isn't that what we're doing? If I put in the samples, one was 47 over 200, the other was 22 minus 142. This was a greater than test. Calculate. The z-score is actually 1.818. You got 1.81. Now, why was it different? Why would what you guys put in your calculator be a little tiny bit different than what the calculator was able to get?
Rounding error.
Yeah, aren't we rounding here? Aren't we rounding on all these guys? Now, if you want to get really fancy, and I have students do this, instead of putting 0.235 here, put 47 over 200. And put 22 over 142. And then put, right here, you'd put whatever that adds up to, 69 over 347. Okay, that would, and if you put that in your calculator, you'd get the exact right answer. I'm not requiring you to do that. If you want to round to 3 to 4 decimals, that's fine. But if you put the parentheses in, it's not like you even have to put it in. You've got this button. Look what it also gives you. What's that guy? So our p-hat weighted, right? That's why it's there. It gives you the 2 individual p-hats. They give you more stuff. What other more stuff does it give you? Oh, just the sample sizes. Okay. Now, how do we do it? Miss Jessica, let's just, as you know, I'll probably mess this up. So let's see how it goes here. All right. I would do parenthesis 0.235 minus 0.155 parenthesis divided by, oh boy, here we go. I'm going to go parenthesis, then I'm going to go square root, okay, 0.202 times 0.798 parenthesis square root, and order of operations, it'll handle this. I don't even need parentheses around this. It'll do the divisions before it does the multiplications. Parenthesis, parenthesis. There it is. Okay. Like I say, if you get really fancy, you put the fractions here, the fraction here, and the fraction here, and we get the same exact answer. Okay. All right, so what are we doing a hypothesis test next? We draw our picture to find our p-value. Remember, the p-value is supposed to be a little bit more than 1%, we're thinking. So we draw our picture. This is 1.82. Is that right? All right, so our picture. Now remember, this is every possible p hat c minus p hat p. What's going to be in the middle of that distribution? Yeah, and this is why I like this way better, right? We're assuming that there's no difference. Send your kid to preschool, not going to do any better in math. That's what we're assuming here, that there is no difference. That's kind of why I like writing it that way a little bit better. There's another reason too, but we'll talk about that later. What did we get as a difference for our little our difference? We got 8%, right? Fill out your whole picture. Some of you still losing points for not filling out your picture. That turns out to be 1.82 z-score standard deviations away. You go to your z-score chart, and I think that comes out to about what?
9.6.
No. Okay, well, look over here now. Don't forget. Right, you got subtracted from 100%. Like 3.44%, I think. So all of you that had your thumbs up, right, the p-value is a little bit more than the alpha level. That's what we expected. 0 was in our confidence interval yesterday. Okay, conclusion, it's the same old three-sentence guy, assuming that there's no difference in the fail rate in math because they went to preschool or not. Right, that's our first sentence. There's a 3.44% chance of getting a difference of 8%. Pretty unlikely. Pretty unlikely you're going to get a difference of 8% with sample sizes that big. So now it just kind of all depends on what you set your alpha level to. That is evidence. I mean, there's only a 3.5% chance of getting a difference of 8%. But if you're going to be a stickler. Now, if this was 5% alpha, right, we would have enough evidence. That would be enough evidence to reject. Since our p-value is higher than our alpha level, we will not reject the null hypothesis. Therefore, we don't have statistically significant evidence to say that preschool is helping in math. Questions, comments? So the big difference is this guy right here changes everything. We have to go find this p-hat weighted and then use that throughout the entire problem. We use them in our assumptions. We have a different formula that factors out that same value. Looks different in our function. Questions, comments?